Hello everyone. Today we are going to discuss uh, one-dimensional finite potential well. Last class we discussed about uh, one-dimensional infinite potential, and then we calculated some eigenvalues and eigenfunctions, their related functions. So in this class we are going to discuss eigenvalues and eigenfunctions of one-dimensional finite potential. Okay, one-dimensional one-dimensional finite potential. Okay, so consider a particle of mass m. Uh, Inside a potential well with a finite barrier of height. Okay, so therefore here I'm going to consider the potential well, uh, that is barrier of a height is h. So this is potential well. So this barrier of this potential well height is v naught. Okay, the height of the barrier, this height of the barrier is v naught. So here I'm going to consider the particle of mass m moving inside the potential well with finite barrier. It's not infinite barrier, right? So the particle is there here, inside the particle of mass m is there. So this particle of mass m, it moving inside the potential well. Potential well height of this box is v naught. So the boundary conditions here I'm going to taking this is minus a and this is plus a. So therefore the potential v of x I'm going to define like this: v naught, where x less than minus a, okay, 1 dg, and 0 in between minus a to plus a, minus a less than x less than a, and again v naught x greater than a. So here two physically interesting cases are there. One is e greater than v naught, another case is e less than v naught. So the first case, we already familiar this type of case, and particle energy is higher than the potential energy, then particle will easily penetrate through that potential. That means the scattering solution will form. Okay, so because here the energy of particle is more compared to the uh, finite potential well, right? So this will easily penetrate through these barriers. So in this case, uh, in case if you want to solve this case Schrodinger equation, what will happen? We are going to check. So this I'm going to consider the equation. I mean case number one. This is case number two. Then I'm going to hear more details. One is the case one. So this case one. So I'm going to give name of this E greater than is scattering solution. Scattering solution. So this is very important. Okay. Now I'm going to solve this uh, equation. Okay. So this is already there, right? I'm considering this case. So for example, this is the height of the potential. In case if you imagine this one, this is the height of the potential energy of x. The particle energy is there here. Compared to potential, the particle energy is higher. This line. Okay. So then the particle is easily penetrate through this barrier. Then we can get here solution like this. Okay, like this. You can get solution. So this is the one important case. So in case if you want to go to solve the using Schrodinger time independent wave equation, so this is already know the Schrodinger wave equation. So d square psi divided by dx square plus 2m divided by h cross square e minus v wave function psi equal to 0. So here the v equal to v naught. This is very important information. Maybe here we forgot to write this information. This is v equal to v naught here. Here also v equal to v. Okay. This is the potentials of different boundary conditions. In case if you try to put v equal to v naught here, then you can get this equation like this. I'm going to modify a little bit thing compared to this thing. Uh, here we're discussing one-dimensional problem, which is why I'm giving the x here, one-dimensional. Remaining two-dimensional motions are restrictions. Okay. So therefore, 2m divided by h cross square e minus v naught into wave function psi equal to 0. So here I'm going to give, we can't write this equation like this. I'm going to modify like this. A square wave function psi divided by dx square minus 2m divided by h cross square v naught minus c wave function psi equal to 0. So after ending, maybe you can get idea why I'm going to using this function here. Okay, a square wave function psi divided by dx square. This one is this entire thing is I'm going to consider the alpha square wave function psi equal to 0. So here we got the second order differential. So we know this second order differential equation solution, right? So we can write easily the second order differential equation. So the solution of this equation is the sinusoidal in the region 1 and region 2. Hence the probability distribution, probability density is distributed over all this space. The particle is not bounded in this case. Okay, this is very important case. Here I'm not writing any solution, because in case if I write here the solution, maybe you can get confusion. One more case is there. So this is not that much important, but you need to know what happened in this case. Okay, so we already explained here. So this is the sinusoidal solution of this differential equation by using these conditions. The probability, this is the probability density is distributed over all the space, right? So hence the particle is not bounded. Particle is not bounded. That is the word is very important. Okay. So the wave function, the in the three regions, this corresponding to the this one. This is, for example, in case if you consider this portion is region 1, this portion is region 2, this portion is region 3, then you can get the entire solution in continuous. And second case is there. That is very, very important. In this case, we are going to discuss each and every step carefully. Then we can analyze these solutions and we can get some eigenvalues and eigenfunction of finite potential. Well, this is very, very important problem. Application of Schrodinger wave equation, one-dimensional problem especially. So in case if you want to solve Schrodinger, this first unit, which means these mathematical tools, then in case if you look any quantum mechanic book, they're solving one-dimensional problem, two-dimensional. After that, they are giving some angular momentum concept. After that only they are solving hydrostatic problem. There is some reason is there, because first we need to solve the one-dimensional problem using the Schrodinger equation. So in case if you try to solve the three-dimensional equation, you need to change the coordinates into the Cartesian coordinates into spherical polar coordinates. For that, we need to study that angular momentum, orbital angular momentum, spin angular momentum concept, which is why I'm going to first discuss one-dimensional problems, two-dimensional problems. In case if you needed that thing, then I'm going to discuss here itself three-dimensional problems also. For that, we need to three-dimensional box is there. Then we can discuss that the potential energy of three-dimensional box, eigenvalues and eigenfunctions of three-dimensional. Okay, here is the second case is a very important thing. Case 2 here. The bounded state solution. bounded state solution. So E less than V naught. This is very, very crucial case. For more clarity, I'm going to write this condition like this: 0 less than E less than V naught. Okay, E less than V naught. So classically, when E less than V naught, which means particle energy is less than the height of the barrier, the particle is completely confined in box, which means minus CA, A2 plus CA region, right? It will bounce back and forth between the walls with a constant. But in quantum mechanically, the solutions are particularly interesting for the they're expecting some uh, yields a discrete energy spectrum and wave function that decay in the two regions. So one is x less than minus a, another region is x greater than plus. So we already know that the diagram, this is diagram, right? So in this diagram, in case E less than V naught, so two cases are there. X, so why I'm writing it x equal to minus a, x equal to plus a region. So two interesting solutions are there. We can get here the very, very interesting solutions. This is region 1, this is region 2, this is region 3. So in case if you try to solve all these three regions carefully, then you can get uh, one information about this case E less than V naught. From that, we can analysis the what is the quantum mechanics going to reveal, what is the classical mechanics to be reveal. Okay, what is the tunneling point, or what is the decay energy or liquid energy. So this type of force we're going to discuss after that. For that, I'm going to calculate step by step in three regions. Okay, so this is my workspace, right? So this is region in region 1. I'm going to try to finish here itself, region 1, region 2. So let us see. Schrodinger wave equation. We know this Schrodinger equation. So first, you need to arrange the potential. Then only you can get the your actual solution. So from the definition, the finite potential, well, right? The outside the box potential energy here, the V equal to V naught. So what is the inside the potential energy of the particle? Either V is equal to V naught. This is the force-free particle, or we are apply some force. In case if you know the answer, just try to comment below. Then I will reply it correctly. So these are the three regions: potential. In region 1, V equal to V naught. Region 2, potential energy. Region 3, potential energy. So here I'm going to use the first region, V equal to V naught. In case if you try to solve the Schrodinger equation by using this potential energy, so we already know that Schrodinger equation d square psi divided by dx square plus in case if you really want to see the quantum mechanical notations, then here I'm going to write the equations is like, okay, for more clarity, I'm going to write the Schrodinger equation like this. Yes, if you try to understand the solution, this is get vector region 1 plus 2m divided by h cross square e minus v wave function, cat wave function in region 1 equal to 0. So if you try to put in place of V equal to V naught, because in region 1 potential energy of the particle V naught. So then we can get here d square divided by dx square, this wave function psi, the region 1 wave function, plus 2m divided by h cross square. Okay. So here itself I am going to use this strict. This is V naught, this is E. Here I am going to put minus. Okay, right? Then wave function is there, that is equal to 0. So this portion I am going to use one value, that is alpha square. D square divided by dx square, wave function psi, minus alpha square, that wave function psi, first region, equal to 0. Therefore, the solution of this equation is, what is the solution of this differential equation? If the minus is there, In case plus is there, what is the solution? You need to observe carefully here the solution when I am writing these solutions. In case if your plus is there, I'm using different solution. Here minus is there, I'm using another solution. Okay, so this I'm going to use the exponential solution. The solution of this equation is wave function psi, first wave region wave function, that equal to the some constant c. I'm going to reveal why I'm using c after that. E power minus alpha x plus d e power alpha x. So this is equation number 1. This is first thing. Okay, then region 2 solution. What is the region 2 solution? In region 2, potential energy is equal to 0. Then what is Schrodinger equation solution? Tell me what is the Schrodinger equation solution. Then we can solve it one by one. First, we need to solve the region 1, region 2 solution and their corresponding the solutions, differential equation solution. Then we can try to put some boundary condition, then we can get the exact values. Don't worry for that. I'm going to explain each and every step. Uh, in region 2, potential energy is equal to 0, right? So in case potential energy is equal to 0, what happened here? Guess if you observe, try to observe d square wave function psi. So here I'm going to use the second, which means the second region solution is 1 for clarity. Okay, d square plus after applying the potential energy, then I can get here this 2me divided by h cross square into wave function psi. Here plus is then I'm using this solution like this. The solution of this equation is this is I got the after putting the equation, then solution of this equation, general solution of this region equation. This is a. So I'm going to go right here one more step for more clarity. I'm going to use 2me divided by h cross square, d square wave function psi divided by dx square plus this one is k square wave function psi equal to 0. So k square equal to 2me divided by h cross square. Then what is the solution of this equation? Second order differential equation solution in terms of x is there. Then I'm going to write this solution a sin kx, because here k is there. This is one dimensional. That is a trick. Plus b cos kx. B cos kx. Okay. This is second solution. This is the second solution. I'm going to remove this function here. I am going to solve here itself this Schrodinger region 2. Okay. For that, I need to give one more bracket. Okay. In region 3, in case if you try to observe what is the potential energy, V equal to V naught. V equal to V naught, right? Same solution, right? Same solution we can get. For that, I'm going to use the boundary conditions here. See, here we got the solution of first region. Observe here carefully what I'm going to apply this here. So we have two boundary conditions. Apply the boundary condition. Okay. So here I'm going to apply the first boundary condition. First boundary condition. So in case if you try to put the I want equation c value and d value, then I can get the easily value. So if you try to imagine here, the x is equal to minus a, this one, x is equal to minus a. In case this potential energy of this well is the, I mean this barrier is minus infinity. In case if it tends to go to minus infinity, then we can use that case minus infinity here. In case if it is tends to go to x tends to go to plus infinity, then we can use the plus infinity case. In that case, what is the wave function here? We already discussed the infinite potential well. In case if infinite potential well is happen outside the potential box, the wave function is 0, right? So here I'm going to use the condition again, equation number 1. At x tends to, I'm not using equal to, x tends to infinity, then we can get wave function psi tends to 0. So then I'm going to try to use this boundary condition in equation number 1. So wave function is 0, right? Equal to c e power minus, in place of x, what is the value? Minus infinity, which is why I'm going to use here the minus to minus plus infinity, plus d e power alpha into minus infinity. Then I can get here the e power minus infinity. Okay. So then what is the value of this one? Is completely 0, right? Then I got the c is equal to 0. C is equal to 0. In case if you try to put c is equal to 0 here, try to put c equal to 0 here, then we can get region 1 solution correctly. Region 1, d e power alpha x at x less than minus a. I hope you understand the solution. Then similarly, you can solve this equation. X tends to, for example, x tends to plus infinity. Then the wave function goes to same wave function goes to the 0. Then we can get here the d is equal to 0. This is 0. Then c e power minus infinity plus d e power infinity. Then from this equation, then we can get d equal to 0. Now you can put d is equal to 0 here. Then you can get one equation here. Wave function psi equal to d is equal to 0. Then c equal to e power minus alpha x. In case if you observe clearly here, I'm applying to, sorry, I applied two boundary conditions. One is x is equal to uh, minus a, x is equal to plus a. Here I'm using tends to infinity value. So this is region 3 solution at x greater than a case. From this equation number 1, I got two solutions. So this is crucial thing. Here nothing is happened. Just listen carefully. I'm going to explain one more time here. This solution I got by solving Schrodinger time independent way, by putting potential energy is equal to V naught, region 1 solution. Then I got this solution. Now I'm going to apply a solution. Two boundary conditions are there. X is equal to minus a, x is equal to plus a. Because of particle potential well is the finite potential well, then I can choose minus value one side and the side is plus value. Okay. So in case if I apply the two boundary condition, then I can get to two different. I know now all three solutions. In region 2, the solution also I know. We already got solution. See, a sin kx plus b cos k. There, yeah, a sin kx plus b cos kx. Okay, we got all three region solutions. Now it's going to very interesting thing. So this is box, right? Potential box. Okay. Here particle is there. This particle will travel like this. Okay. After collision, this will it return back here and goes like this. Only x axis, right? Okay. It's going forward and backward direction. Oscillation. Sine function and cos function is there. Here, wave function must be continuous at boundary conditions also. Here also, wave function must be continuous at boundary conditions also. This is x equal to minus a, boundary condition is x equal to plus a. By using classical mechanics, we can't explain this leaked energy or tunneling energy. Only explain by using quantum mechanics. This one is tunneling energy or leaked energy of this. So in case if you try to understand this thing, that is very good. So here itself, I'm going to explain this thing in conclusion of this topic by using a single harmonic motion, simple pendulum. And whatever we got this result, both this result we can compare the classical mechanics and quantum mechanics. Yeah, definitely I'm going to give guarantee you can understand very well what is the difference between the classical mechanics and quantum mechanics. Okay. So here, by this explanation, the wave function in region 2 can either be symmetric or antisymmetric about the origin. Hence, we can match either symmetric or antisymmetric wave function of region 2 to the wave function if region 1 and region 3 at the same time. So according to this solution, I am going to arrange this solution like so. In region 2, the wave function symmetric is there, antisymmetric is there. So which part is going to match? I don't know. Present I don't know. Huh? Region 1 solution. Which part, either symmetric or antisymmetric, we will match into the region 3 solution. We want to find that first. Region 1, 1. Region 2 is symmetric and antisymmetric solution. Here the two functions are there. One is sine function, another one is cos function. So maybe you already aware of this y is equal to sine x. So y is equal to cos x. So by using these two functions, which one is symmetric, which one is antisymmetric function? The sine is the symmetric function, right? So whatever fashion will travel in x-axis, sine function. What is sine 0? Sorry, cos 0 value. Sine 0 is equal to this cos, right? Cos 0, 1. Okay, like this. Whatever fashion will travel in x direction, the same fashion, same frequency, same amplitude will travel the minus x-axis values. Minus x-axis, this is plus x-axis, right? This is frequencies and amplitude exactly match. So therefore, here I'm choosing cos is symmetric function solution, sine is antisymmetric. Definitely y is equal to sine x will not match plus x direction values minus x direction values. Therefore, I'm going to write the solution like this, symmetric solution. This is very important information. Here, which wave function is matching here. So why we are going to write this solutions, two solutions. One is symmetric solution, symmetric solution, symmetric solution. Wave function psi of x equal to z. Okay, I know three solutions, right? This is d e power alpha x less than minus a. Okay, b cos kx. This is minus a less than x less than or equal to a region. C e power minus alpha x greater than a. You got my solution? So here I am taking the symmetric function, right? In case if I consider this wave function, this wave function is there right here. This wave function, wave is traveling. Suppose this wave is traveling like this. Okay, suppose this wave function, in case if it is symmetric, this will match uh, cos function of this continuous function. Here some exponential function is there. This exponential, this d e power alpha x function is match b cos ax function here region 2. Then it travel at x is equal to plus a region. It will match here the other function e power minus alpha x function at region 3. Okay, so this is the solution. Now I'm going to apply the original boundary. Yeah. So what is the original boundary condition? When, in case if you try to apply, when x equal to minus a, the first boundary condition I'm going to apply, what will happen here? X is equal to minus a region 1 solution and region 2 solutions are equal. Okay, because wave function is continuous at boundary conditions also, which is why this wave function is equal. Wave function is continuous at boundaries simply. Therefore, I am going to write this equation like this: b, d e power alpha x equal to b cos a x. Now I am going to using boundary condition x is equal to minus a. D e power alpha in place of x minus a, at equal to b cos k in place of x minus a. We know cos minus theta equal to cos theta because of a symmetry function, right? Okay. There is no changes in values. Therefore, here I am going to write this equation like this: d e power minus alpha a equal to b cos k a. So now I am going to differentiate this equation. The differentiation of this equation, I am going to work some differential equation. So it's better to give some equation numbers, then only we can understand these things are very well. So okay, no problem. If you want to use an equation number, you can use from starting, but this time it is very difficult. So which is now I'm going to differentiate this equation. This equation, this box equation is there, right? This equation I'm going to differentiate with respect to. Here I'm going to write that equation. In that case, take derivative, okay, with respect to a. Okay, this equation, this equation. With respect to a, we can derive it one time here. What will get here? E power minus x, remaining thing minus alpha. Alpha is there, so therefore minus alpha d e power minus alpha a equal to this one. B is constant cos ka. So therefore remaining thing here, the with respect to a, right? K is there. So here I got the cos differentiation minus sin ka, right? So minus k b differentiation of cos minus sin ka. Maybe I am using these equations here. This is a equations number are necessary, then only we can understand these things very well. Okay. Okay. Equation number one. Equation number one. This is equation number two. Okay. The equation number two. You can assume if this is this two, or maybe equation number two. This is equation number three. Okay. Okay. Very good. So this is equation number three prime. Maybe this is equation number four. Okay. Now we can use this equation number four divided by equation number three prime. Then what we'll get? Minus minus cancel, right? Minus minus cancel. Here minus is there. That minus is cancelled. So minus d alpha we forgot, right? This minus is there. Here the minus minus is cancelled. This minus, right? Okay. Remaining thing we can write equation number four divided by equation number three prime. Then we can get this thing. This one and this one cancel. Then alpha only. Then that equal to k tan ka. Okay. Then I'm going to multiply here alpha into some amplitude a, constant a, small a, both sides a tan k a. I'm going to design this equation like this: gamma equal to beta tan beta. These are very very important things. This is equation number 5. Therefore, beta equal to ka, gamma equal to alpha a. So this is the symmetric solution. Now I'm going to solve the anti-symmetric solution. What is the anti-symmetric solution? Sine function, right? So for that you need to match the sine function. So this is a lengthy derivation. So you need to be careful during this derivation. So these are all the MSc topics, not is useful for CSIR NET. In case specifically any CSIR class is there, then I'm going to mention this CSIR class, the title of the videos. Okay. So these are all the syllabus of MSc student. Quantum 1, 2, 3 is there. So this is first semester quantum mechanics. Okay. This anti-symmetric solution psi of x equal to d e power alpha x, means x less than minus a region, a sin kx minus a less than x less than plus a, c e power minus alpha x, x greater than a. So this is the symmetric solution. Now I'm going to apply the second boundary condition. We know that secondary boundary condition. What is second boundary condition? X equal to plus A. I'm going to apply the second boundary condition. So in this same explanation, right? So in second boundary condition also region 2 solution will match region 3 solution. So therefore, the wave function must be. So for simplicity, I'm going to use these two conditions. Okay, these two. You can use any one of these equations, right? The common this one. This is region 2. You can match the solution or this equation or this equation. Okay, so you need to match the region 3, right? So for that, you need to use the region 3 solution. Okay, these two. So therefore, the region 2 solution is equal to region 3. So what is region 2 solution here? In this case, antisymmetric case, A sin k x equal to c e power minus alpha x. Now you try to substitute this boundary condition x is equal to a in this equation, then we can get here the a sin k a equal to c e power minus alpha a. Again, I'm going to using this equation. Equations are very important here. This is equation number 7 and this is equation number 6 and this is equation number 7 for important, which is why okay, these two are same, right? Next equation, it is better to use equation number. Okay, I'm going to differentiate this equation number. Both are same, right? These two equations. Just wait 1 minute. Okay, now I'm going to take derivative with respect to a, this equation. Okay, then we can get this equation, right? This is a k cos k x at equal to c e power minus alpha x. This one with respect to a, we didn't substitute. After substituting a only. Okay, sorry for an interruption. Just wait. Yeah, first you need to apply the boundary condition, right? Whenever you solving this type of equation, just be careful. C e power minus alpha a. Okay, so to maybe you can better to use this equation here. This is equation number 6. Okay, now you can take the derivation derivative with respect to a, the 6th equation. Then we can got here this minus alpha c e power alpha a, this portion. Then this portion is a k cos k a. This is equation number 7. Now you can divide one to equation number 6. Equation number 7 divided by equation number 6. So k cot ka equal to minus alpha. Then ka cot ka equal to minus alpha. Therefore, the beta cot beta equal to minus gamma, right? Okay. This is equation number 8. You can take equation number 8 like this. Maybe this is equation number 8 prime. Then if you try to add this beta square and gamma square, beta square plus gamma square equal to, so what is beta square? We know that k square a square plus alpha square a square. Therefore, here I'm going to write k square plus alpha square into a square. Then we know k square value already 2me divided by h cross square plus 2m v naught minus e divided by h cross square into a square. So by cancelling these two equations, remaining equation is beta square plus gamma square equal to 2m v naught divided by h cross square to a square. In case if you clearly observe this equation, this is one important familiar equation we already know, right? This is uh, it is look like a circle equation. X square plus y square is equal to r square, right? Then what is the r square value? 2m v naught divided by h cross square into a square. So therefore this r square, this is the radius. So where this r, this is not gamma, okay? Just r, okay? R equal to, so root of. So it is better to use root of root of 2m v naught divided by h cross square a square. So that is your wish. In case if you want to write this a square outside the square, then you can use a. That is better. Or else you can write like this: r equal to 2m v naught a square divided by h cross square. This is far better than anything. All power 1 divided by. So this is xy plane with radius r. So now we are going to discuss the one by one solution of this finite potential. Okay, this is the radius of the circle. Okay. So now we are going to discuss uh, the allowed energy levels of different equations. For that, we need to solve equation number 5, this equation, and equation number 8. Okay, not this one, 8 prime. So first one is the equation number 5, gamma is equal to beta tan beta. So the equation which I got some solution, beta equal to, sorry, gamma equal to gamma equal to beta tan beta, right? So we want to draw the graph between beta tan beta against this beta along with the circle of radius this r for different values of this v naught a square to this one. As beta gamma can have only positive values. The intersection of the two curves in the first quadrant gives the energy levels uh, n equal to, for example, 1, n equal to 1, 3, 5, and so on. So therefore, we can get the beta 1 and beta 5 values. Okay, beta 1 comma beta 2 comma beta 3 values. For that, we already know the beta square equal to a square, a square. So then k square is equal to 2me, right? 2me a square divided by h cross square. Therefore, En equal to h cross square beta suffix n divided by 2m a square. First, I need to draw the curve, then we can go and discuss the remaining thing. Okay, x-axis, okay, now it is enough. So in x-axis here I'm going to so y-axis gamma equal to alpha a, so this is beta value, beta equal to k. So here we got the radius, right? Radius of this x square plus y square is equal to r square. It is look like a circle equation. So this is beta and gamma plane. This is beta and gamma plane. Now you can understand this equation. Importance. Beta square plus gamma square is equal to, I got this 2m v naught a square divided by h cross square. This is r square. So here in this graph we can get this some radius. Okay. So therefore it is better to use different type of equations here. For example, this is pi divided by 2. Okay, this is pi, and this is this line. Okay, 3 pi divided by 2. Okay, good. So here I have gamma is equal to beta tan beta, and one more equation is there, that is gamma equal to sorry minus gamma equal to beta cot beta. So we need to draw these two equations in graphical representation, then we can understand. First I'm going to draw this equation. So this is tan graph beta tan, and here is this is beta tan. Okay, okay, no problem. So this curve is beta tan beta equal to gamma. And this curve also beta tan beta equal to. So these are the beta tan beta value. Then minus gamma. So here minus is there. Okay, then we can get these values in opposite directions. This is okay. No problem. So this curve is minus beta or beta equal to gamma. and this is important. Okay, this is minus beta cot beta equal to gamma. So first you try to practice this y is equal to tan x graph minus y is equal to cot x graph. So first you need to understand y is equal to cot x graph. You can draw y is equal to cot x. Then you can draw the y is equal to minus cot x graph. Then you can get this answer. Okay. So minus beta cot beta equal to gamma graph. Then only can understand this thing. So these are the curves from graphical representation I got. So radius also there here. This is the radius. So this is the radius. Okay. This one and one another radius. This one is another radius. And this one is another radius graph. Okay. This is n equal to 1, n equal to 2, n equal to 3, n equal to 4. So these stars are there, right? These dots, this dot, this is dot, this is dot. These are the symmetric functions. And the stars are there, right? Stars are anti-symmetric intersection. Anti-symmetric intersection. Uh, these are dots. These are symmetrics. Okay. Uh, this is anti-symmetric. Symmetric intersection. This is symmetric intersections. Two curves are joining at one place. Okay, intersection is there. So therefore, here I'm going to find these energy values. So beta square is equal to k square a square equal to 2m e square. From this equation, en equal to h cross square beta n square divided by 2m a square. Similarly, we can get energy values of gamma equal to, which means minus gamma equal to beta cot beta. The energy values gives n is equal to 2, 4, 6. Okay, n is equal to 2, 4, and 6. Well, did you understand this 2, 4, 6 values here? This is 2, right? Symmetric values. Minus beta cot beta equal to gamma. The first intersection is appear here. The n equal to 2 here. This one. This is n equal to. N equal to 4 is there here. Okay. See here. N equal to 1. N equal to 3. Okay. N equal to 5. So these are the reasons. So beta, these values. After the find out this graph only, you can understand this. N equal to 1, 3, 5. So why I am taking this n is equal to 1, 3, 3. From graphical representation, I took this. N equal to 1, I got here. N equal to 3, I got here symmetric function. Symmetric function intersection. This is anti-symmetric function. N is equal to 3, 4, 6. Sorry, n is equal to 4, 6. See here, n equal to 2 here, intersection. Next intersection is there here. This one it is going on. This is the fourth one, antisymmetrics. Next one is 6. Okay, like that you can understand. Okay, so gamma square equal to gamma square equal to alpha square a square, right? So I know alpha value 2m v naught minus e divided by h cross square. This is alpha square value and remaining thing a square. From this equation, I can write like this equation v naught minus e equal to this is gamma square h cross square divided by 2m a square. Therefore, En equal to here. The extra potential is there. This is gamma, not r. Okay, divided by 2m a square plus v naught. So for the particle, the number of bounded states depends upon the height and width of the potential. Okay, through the factor, this factor v naught into a square. This factor v naught into a square factor value. So first intersection in between from this graph. So first intersection, one intersection is there right here. First intersection. If 0 less than radius less than pi divided by 2 from this graph. Okay, see here in between 0 and pi divided by 2 I got one intersection. So in between pi divided by 2 and pi, how many intersections are there? One symmetric, one antisymmetric, two intersections are there. So pi divided by 2 radius and less than pi. Three intersections are there in between pi less than radius less than 3 pi divided by 2. See here. This is 3 pi divided by 2. In between 0 and sorry pi and 3 pi divided by 2 symmetric function is there. Anti-symmetric function is there. Symmetric function. So therefore, the energy level of this one-dimensional finite potential well from this analysis can go and find this energy levels easily. This is potential energy V of x. So first n equal to 1 from this graph. From this graph, this is n is equal to 1. Equal to 1. So only one intersection is there, that is symmetric. You can understand this one like this. Next, n equal to 2 here. N equal to 2 from this graph, n is equal to one symmetric, one anti-symmetric function is there. So we need to draw one symmetric, one anti-symmetric function. Okay. From here, and I can add this. Okay. Next, n equal to 3. N equal to 3. N equal to 3. So three intersections are there in between pi to 3 pi divided by 2. See here. Symmetric, anti-symmetric, and symmetric. So in energy levels, One symmetric function is there, two anti-symmetric functions are there. So yeah, okay. This is continuous. There is no break here. Okay? So like this. These are the first three bounded state eigenfunctions of the finite potential. Right. So especially in the case of E less than V naught case, E less than V naught case, bounded state solution. So in region 2, so we are divided in three type of regions, right? Here, this is, for example, if you consider this one is region 1 and region 2, like that only we considered during the solution of Schrodinger equation, right? So region 2, the wave functions are similar those in the potential well with the infinite wells, right? However, they have tiles in the uh, region 1 and 2. We clearly observe some leaked energy also there here in region 1 and region 2. So at the points x is equal to, this is minus 1, x is equal to, sorry, x is equal to minus a, x is equal to plus a. So only a classical tunneling points for the well. Wave functions have the tiles beyond the classical tunneling points, uh, mean a finite probability for particle to be outside the well also. In other words, we can say like this, the quantum mechanical particle has a tunnel or leaked into the classical forbidden region. This classical forbidden region. So this is all about one-dimensional finite potential well. This is very, very important. From this topic, and they can frame many questions CSIR GateNet examination. Okay, they are giving some bounded state potential energy. Then they are asking to find the energy levels of this quantum state. Okay, so they are giving different type of bounded state potential energy values in examination point of view, and they are asking to find the energy levels of according to their question is framed. So like that they are framing some questions. So later we can discuss the each and every problem after complete of this class lectures syllabus. Next class I am going to discuss I think probably the potential step barrier.